Okay, in this last video, that sort of, this is all the sort of important reactions and recipes and stuff. And obviously it's not meant to cover everything, but it's supposed to give you a foothold into some reasonably complicated topic. Let's take a look at how we form carbon-carbon bonds. So another really common way to ask synthesis problems, and you'll see this on our quiz for sure, is to just give an alkane or give some simple starting material. Sometimes it's not always an alkane. But as I kind of talked about in the last video, alkanes are almost like a worst case scenario. And just sort of, how do we connect these guys together? Okay. And this is a little bit harder than what we saw in the last video. So in the last video, it's like, okay, well, we've got this recipe where we can take an alkane and we can do a series of functional group transformations on it and say, okay, I'm going to make this into a haloalkane. Oops. I'm going to make this into a haloalkane. And then I can make that into an alkene. And I'm just trying to string together a whole bunch of things that I've memorized. Not that that's easy, because it is a lot of stuff, and it does require some logic. But these carbon-carbon bond-forming reactions require all of that, plus this additional insight into sort of understanding where in the molecule it makes sense to connect things and how they're connected. It's just a harder concept to kind of grasp. So for carbon-carbon bonds, the key thing to recognize, or one of the beginning things you can recognize for OChem 1 at least, this isn't true in OChem 2, is that if I form a carbon-carbon bond, that means that somewhere inside of my reaction scheme, my synthesis scheme that I come up with, I'm doing this reaction. I'm going to take an I'm going to take an alkyne, I'm going to deprotonate it, and then I'm going to take a primary alkyl halide, or something with a leaving group. It doesn't necessarily have to be alkyl halide, but that's the most common way to see it. I'm going to connect those together. So I know, before I even kind of start parsing, like, okay, I've got this, like what recipe do I need to think about, and like where do I break all this stuff at? Before I get to do any of that, the first thing you want to do when you sort of see a problem where you're forming a carbon-carbon bond inside of this class is to write this down. You're going to use this. Okay, and you've noticed I put the generic groups on here, R prime and R, meaning that these could really be anything. But if I'm going to form a carbon-carbon bond, it's going to require that reaction along the way. Oops. There we go. Okay, so let's move this down. So this reaction we know is going to be important. I'm going to put it up here in the right-hand corner. And now let's come down here. Let me make this a little bit smaller. Let's make this a little bit smaller as well. Okay. All right, so all I'm saying right now is just that this over here is going to imply the use of this reaction over here. And so I put that reaction up in the upper right so that I free up some of my working memory. And if I get confused during this problem, I can, for you guys, if you get confused during this problem, you can go and look at that reaction and sort of break it apart there. I would even say go so far as to number the different things even in this little fundamental piece here. Because that is part of the challenge. Oh, you got double numbering there. 3, 4, 5, 4, and 5. Okay, that's part of the challenge here. It's just kind of seeing where those things connect. And I've done this in previous videos, and I think it's still handy. If I label that, that's that carbon there and carbon 4, and then I can label this other side as carbon 3. And we'll see that carbon 3 and carbon 4 sort of come together and mate to form the carbon-carbon bond in this molecule. All right, so that is our reaction. You make sure that you really understand what's going on here. So before you even attempt to kind of get into these carbon-carbon bond forming reactions, your very first step is to really understand this canonical example of forming a carbon-carbon bond through an alkyne. So that would be your starting point, is just practice that. And you can make up your own practice. The main thing is just to be able to follow what's happening with the carbon atoms as you connect them. What's leaving, you just want to be able to follow kind of like what part of the carbon fragments which pieces of the carbon fragments are being attached, and like what are you eliminating? So and I don't mean eliminating in the chemical sense. I mean like what atoms aren't getting carried through. So in this particular example, the orange carbon, carbon 3, is being attached to the green carbon, carbon 4. Let me see if I can highlight that while I talk. I've got orange carbon 3 here, and I'm connecting that to this green carbon 4. And then after they're connected, you can see them over here that I've formed a carbon-carbon bond. They're stuck together now, right? And the thing that's gone, the thing that's left, let me find a good contrasting color here. The thing that's left is this bromide. Bromide's gone. Okay, that's the only thing that doesn't show up in the product. That's whatever. That's the leaving group for the SN2 reaction. All right. So anyway, before you sort of start trying to hack at these problems, which are hard, make sure that you really understand this alkylation reaction in the upper right-hand corner. Okay, now let's look at this. Let's look at the task at hand here. So I've got 3 carbons here. I think the first thing to do is just do like a reality check to make sure that the problem makes sense. Oh, and you can. It's like subconsciously I knew that something was wrong with this problem. Yeah, what we see here is I'm actually missing a carbon. What I meant to do is have 6 carbons long. There we go. Okay, so we've got 1, 2, 3, 4, 5, 6 carbons. So the obvious thing that probably happened there is that I've taken 2 of these propane molecules and connected them together somehow. Now, because I'm in organic chemistry 1 and I only know one carbon-carbon bond forming reaction, I immediately think of this reaction over here, which I've studied really well and I'm totally prepared to use in this problem. Okay, so what are we going to do? There's a lot of different ways to think about this, and I know I've worked these similar problems in other videos from the workbook. And it sort of depends on how you like to work at problems. I'm trying to think of arguments for not doing it this way, but I think one way or the best way, sort of the most foolproof way, is to try and figure out, try to work backwards. And I know that can be a little bit challenging. So one way to do it is to kind of work back to what this used to be. So using retrosynthesis, I can sort of think backwards and look at this as an alkyne. And that's my recommendation. So I'm going to work it a little bit like that, and then I'll show you kind of how, if you try and just go at it from the other direction, that can sometimes work out for you as well. Okay, so going in though, I'm just going to mark. So this molecule is pretty symmetric. I'm going to mark this carbon 3, and I'm going to mark this, just following along with what I did on the sort of the canonical example over there. That's going to be carbon 4. So once I sort of have this highlighted in my molecule, if I really have gone through and studied this really hard, now I can just sort of relate that molecule, this molecule that I've drawn, let's see. I can relate this molecule that I've drawn here back to this new molecule. And these are really similar. There are obviously more complicated examples where it's not going to be this easy, but this is definitely your starting point. Okay, so yeah, how should we think about this? Yeah, I guess, like in terms of recipes, it's almost more helpful to think about this one in reverse. So, I've drawn it in the forward direction, but like, what if we thought about this one in this direction? this is probably the more useful way to memorize the alkyne the carbon-carbon bond forming reaction, is that this starts, and now I'm drawing it as the alkyne, not the deprotonated alkyne, but it starts as this. And ends. Whew. Ends up as that, but we're trying to think backwards here, and so you can almost, let's see, if we can, I'm trying to think of this as, if we go ahead and we number this, we can come over and we can carry some of that numbering over to our other side. So yeah, these groups are always going to be different, but this joining that I've done here, like this the colors here. This part where I've joined it, all of this, that part's going to be consistent, and I think it's, what you're looking for here is you're looking for consistency. You don't want to be in a position where you're like trying to figure this stuff out every single time you come across a problem, because that's exhausting, and there's really no reason to continuously reinvent the same thing over and over again. All right, so, but this is nice because now I can look at this and I can say, I even have the numbering identical. I can say, I know I broke this at carbon 3 and 4, and what that means is that, what that means for me is that when I look here, right, my alkyne is between 3 and 2. And the same thing is going to be true over here. I can take the alkyne and draw it between 3 and 2. And so that holds. Okay? And I'm gonna put the protonated version. Hopefully it's clear like how that gets deprotonated. All you have to do is treat it with LDA. And then on the other side, okay, we're missing one little piece here. So yeah, so that's that carbon. And on the other side, carbon 456, this other carbon fragment, we know that if we come over and we look at look here, like that's, sorry, the colors are not super great. If we look at carbon 4 and 5, that's going to be carbon 4 and 5 here. Actually, let's say, just to be consistent with our other example, we'll just say that that's going to be carbon 4, because we're not as interested. So for the alkyne, we have to worry about carbons 2 and 3 because we're forming an alkyne there. Here, what I'm calling carbon 5 over here actually isn't really that important because that's just part of the R group, and that thing is variable. So I'm going to get rid of the coloring on that and say that we're only really concerned with carbon 4 here. And so we come back up and we look at carbon 4 up at the top. And so 5 and 6 I don't really care about. Nothing's going to change about those. But I do know that carbon 4 must pick up a halogen if I'm going back in time. There we go. Yeah, so I do know that carbon 4 is going to pick up that halogen there. Not carbon 4. Yes, carbon 4. Yeah, carbon 4. Good. Yeah, so carbon 4 is going to pick up a halogen there. Okay. Sorry, my coloring scheme and numbering scheme got beyond me for a second there, but I think it's consistent. Okay, so yeah, but now I've gone back and as long as I studied this reaction up in the upper right, then this decomposition of this molecule back into this is not super difficult. And you might not want to go directly between those. I guess actually it's probably fine. It's probably fine to do this for this particular example. You don't necessarily have to go immediately to the alkyne. like maybe if you want to go more stepwise, you could say, okay, well I know that, and this is how I've worked it in other videos. Maybe it's a better way, I don't know. I know that 1, 2, 3 is going to be, I'm going to form this, 4, and then 5, and then 6, and then break it up from there. That's fine too. It doesn't really matter. This is maybe better just because it helps you keep track of things more closely, like it's better for bookkeeping. But you just find a method that works for you. But however you end up here, it's going to come from understanding that reaction that we started out looking at. This reaction that I've, up here in the, let me erase all this. So all of your carbon-carbon bond forming thinking patterns are kind of based around that reaction in the upper right. And then once you kind of get here, which is hard, this is a hard thing to do, that's why I'm sort of taking my time and putting like a million colors down on the page. But once you get here, it's not that bad. So now what we see is that we can use our recipes from our previous, that we previously learned. We can take this and push this to an alkyne, and that's covered in detail in a different video called alkyne recipe. And we can take this and we can push that to an alkyl halide, and we're good. Yeah, what happens in this last step here? So I'm just, this part I don't want to have to keep, because these get really long. I don't want to make the video super long. That's covered in the other videos, so I'm not going to go through that. Let's focus more on like what's going on in the alkyne recipe. And here we have a haloalkane recipe. Let's focus more though on what's going on with the carbon-carbon bond forming reaction, like kind of some things that can catch you off guard there or be difficult. And we're not going to really focus too much on these. And I'll just kind of shrink these guys down and put them off over here in our general kind of recipe side of the page, I guess is how we're treating that right now. But yeah, like let's go back up here. So when we finally, let's say we get to this step, so we've made our alkyne, and we've made our alkyl halide, and we've put it all together. And if you really want to see some like full, like those problems fully worked out in the forward direction, go back to, I'm trying to remember like the workbook problems from, I think maybe it's actually from this chapter. I think I worked through like just some full problems where I sort of show you how to put everything together at the end. So, but yeah, let's say we get to this point. And the whole time, especially if I'm on an exam, I'm being really careful to number everything, because it's just so easy to lose a carbon and just be super confused. Okay, so I get here. So once I've made this, in this original problem up here at the top, I'm just making an alkane, excuse me. And alkanes are kind of tough just because it like removes a lot of information from the molecule. It doesn't necessarily, it's not immediately obvious unless you look at the starting material, but it's not immediately obviously like what was done to this. Because alkanes, just there's not a lot of, if you're looking at them in terms of like, their nodal inputs on those graphs that we look at, they're just kind of dead ends. They have like, 1 or 2 arrows in and like 1 or 2 arrows out. And so they give us the least amount of information about, I don't know, what the molecule started out as. There's a lot of ways that there's only I'm saying that in a really poor way. I guess for me, when I look at this molecule, it's just sort of like a featureless landscape, There's nothing really happening here. It's all CH bonds. And that's just not very telling for me. Whereas if I look at a molecule like this, I know like different ways to make alcohols. I can sort of infer that there was an alkene there and where that alkene might be. So the functional groups kind of give you a little bit more information than just having an alkane. But yeah, how do I get between these two things? I can just take H2 and add in some platinum or something and hydrogenate away the triple bond. So what's happening in that reaction, and we've gone over this before, is just like right here where I've marked in orange, like carbons 2, 3, I'm taking and I'm just adding hydrogen on. So those are in the alkyne, there are no hydrogens there. So I'm adding a couple of equivalents of alkyne. And then, yeah, so here now those carbons are now hydrogenated. They've taken on a bunch of hydrogen.